Now that we understand what electricity is and how it flows through different materials, let's take a look at electrical circuits and the three variables that govern how they work: voltage, current, and resistance. An electrical circuit is a system of conductors and components forming a complete path for electrical current to travel. Every circuit has three properties: voltage, current, and resistance. And if you understand the relationship between these three variables, you can start to understand how circuits work. Current is the flow of electric charge. It's a measurement of how many electrons pass a certain point in the circuit in a given amount of time. We measure current in a unit called amperes, or amps for short. Electricity can be a little tricky to visualize since it's an invisible force, but electricity flowing through a circuit behaves very similarly to water flowing through a pipe, so it helps to think about electricity as flowing water. In this example, we have a tank providing the pressure. This is like the battery in an electrical circuit. The water flows through a pipe, which acts like the wire in our electrical circuit, and the pipe connects to a faucet, which acts like an electrical switch that can turn the flow on or off. When the faucet is off, there is no flow, but when the faucet is turned on, the water is able to flow. This is just like flipping a switch in an electrical circuit. It allows the flow of electrical current. So again, when the switch is off, there is no current, but when the switch is on, there is current. Simple. Originally, it was assumed that current flowed from the positive side of the battery through the circuit and into the negative side. But this isn't actually what's happening. The negative side of a battery has a surplus of electrons. Those electrons actually flow from the negative end of the battery through the circuit and into the positive end of the battery. The truth is, it doesn't matter which way the current is flowing. Electricity moves through a circuit instantaneously, so it doesn't matter whether we think of current flowing from positive to negative or negative to positive, as long as we are consistent. Both conventional current and electron flow models are used, so it's common to see circuits diagrammed in both ways. Science disciplines tend to use electron flow, whereas engineering disciplines use conventional current. Since this is an engineering course, we'll be trying to stick to conventional current. Voltage is the force or pressure that causes current to flow through an electrical circuit. Without voltage, the electrons in a conductor would simply stay put. The amount of pressure in an electrical circuit is measured in volts. Let's compare a circuit with a water pipe again. In this system, the tank supplies the water pressure. A battery does the same thing in an electrical circuit. It provides the voltage needed to make electricity flow. When the faucet is off, is there any pressure? Yes, the water is putting pressure on the inside of the tank, the pipe, and the faucet. When the faucet is turned on, is there any pressure? Again, the answer is yes. Whether or not current is flowing, there is still pressure on the tank, pipe, and faucet as long as the tank or battery is connected. In an electrical circuit, the battery provides the voltage that will push current through the bulb when the switch is turned on. Resistance is the opposition to the flow of current within a circuit. The amount of resistance in a circuit, or in an individual component of a circuit, can be measured in ohms, which is abbreviated in formulas using the uppercase Greek letter omega. To better understand resistance, think about what would happen to the flow of water from a faucet if a rock got stuck in the pipe. The amount of water flowing through the faucet would decrease. Just like when electricity encounters resistance in a circuit. All materials have resistance. Conductors have little resistance, while insulators provide a lot of resistance. Some electronic components, such as resistors, have a very specific resistance because their job is to reduce the flow of current by a specific amount. When a resistor is added to an electrical circuit, it slows the flow of current. In this case, it makes the bulb dimmer. Some electrical components are designed to receive an exact amount of current, and too much could damage them. So resistors might be used to reduce the current to a level that will work better for the components in a circuit. A multimeter is a tool that can measure the electrical properties of a circuit, including voltage, current, and resistance. To measure voltage with a multimeter, the dial should be turned to the appropriate voltage range. Voltage is measured across the component, so one of the wire leads is touched to one side of the component being measured and the other lead is touched to the other side. The positive and negative signs represent polarity and flow, so the red or positive lead should be toward the positive side of the battery, and the black or negative lead should be toward the negative end. If these positions are reversed, the multimeter will read a negative voltage. The voltage reading can be different between any measured components. Measuring the voltage across the battery should tell you the total voltage supplied to the circuit. Measuring current with a multimeter is done a little differently. First, the dial is set to the appropriate current range. Then the circuit is broken and the leads of the multimeter are used to complete the circuit. The current has to flow through the multimeter to take this measurement. To measure the resistance of a circuit, first you must disconnect the power source. Measuring resistance with the power connected can damage the multimeter. Even turning the dial past the resistance range while power is connected can blow the fuse in the multimeter, so make sure the power is disconnected before taking your measurement. Once that's done, turn the dial on the multimeter to the appropriate resistance range. Then the resistance can be measured across the components, just like we saw when measuring the voltage. The multimeter supplies a small amount of current to one lead and measures how much is received by the other lead in order to figure out the resistance of a component. Voltage, current, and resistance are tied together by a mathematical relationship called Ohm's law, which states that current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. In other words, if we know two of the three quantities, we can solve for the third. It helps to know your abbreviations for these three variables, as well as their units of measure, and the abbreviations for those units of measure. Ohm's law can be written three different ways, depending on what we need to figure out. This chart shows the relationship between voltage, current, and resistance. An easy trick is to cover the variable you want to find. This will show you the operation you need to do to calculate it. To find voltage, we cover the V, and we can see that I times R, current times resistance, will give us the voltage. If we want to solve for I, current, we can cover it up, and we see that if we divide the voltage by the resistance, we can find the current. If we want to solve for the resistance and we cover up the R, we find that if we divide the voltage by the current, it will give us resistance. Ohm's law works when all of the variables are in whole units: volts for voltage, amps for current, and ohms for resistance. However, these units utilize metric prefixes when they occur in very large or very small amounts. For example, 3.3 kiloohms might be used instead of 3,300 ohms, or 2.5 milliamps might be used instead of 0.0025 amps. When calculations are done using Ohm's law, it's important to convert your values into like units before performing your operation. Dividing volts by milliamps will not equal the correct amount of ohms. Let's see an example of Ohm's law. The flashlight shown uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? In this example, the voltage is known, and the resistance is known, and we need to calculate the current. Ohm's law tells us that the current in a circuit is equal to the voltage divided by the resistance. Since these values are given in whole units, we can plug them right in. 6 volts divided by 150 ohms equals 0.04 amps of current, which we could express as 40 milliamps. Now that we know the basics of the relationship between voltage, current, and resistance, you should be able to do a few practice problems with Ohm's law. In our next video, we will take a look at the different types of circuits and see how their behavior changes when they're configured in different ways.